Hello, chemistry students. If you're watching this video, it means you already watched the videos on predicting products covering synthesis, decomposition, combustion, and single replacement reactions. If you haven't seen those videos, please make sure you go back and watch them first. So we're going to be going over double replacement reactions today. You'll need your notes, and you also will need your activity series and solubility table. The other side looks like this. That's the activity series for the single replacement reactions. But we're going to be focusing on the solubility table for here for the double replacement reactions. Okay, so let's start. Let's look at this first example. If we have potassium iodide and lead 2 nitrate, you know it's lead 2 because of that 2 there, what will the products be? So the first thing we have to do is we have to break it up into our different ions. So if you look at this, potassium iodide, well, that is really a potassium 1 plus, because it's in column 1, 1A, not bimetal, and that's iodide 1 minus, it's a halogen halide in group 17, so that's how we get that formula. And then we have lead 2 nitrate. That one is going to break up right here, so this one's going to come here. I know that it's lead 2 because if you undo your crisscross, the 2 came from lead, and the unwritten 1 right here came from nitrate. So we have a Pb2 plus, and there are 2 nitrates, so make sure you pay attention to that too. So we've got to figure out what are the products going to be. So all these ionic ions have a cation and an anion. If you've done this, we always write the cation first and then the anion. This is a double replacement. If you flip back in your notes to when we saw our dance, that means everybody switches partners and gets a new partner. So with our ions, the metal has to go with a new nonmetal. So our first metal is potassium, so that's going to be K+. So I say I'm going to have a K+, and I need to get with a new anion, so that's going to be my NO3. Now I'm not writing the 2 in front. I just know that these are going to be a new compound, and then I need to get another new compound. So lead is left over, so I'm going to have a Pb2+, and then the other anion I have left over is an iodine, an I1 minus. Okay, these are not your final formulas. I'm just thinking about if I dissolve these compounds into water, they kind of make this big ionic soup, and then they're going to recombine and get new partners. So to figure out if this reaction goes through, we have to look at a couple things. So let's actually get these written as a correct formula. So if we have K plus an NO3, so that's going to be, I should write this up a little higher. Hold on. So that will give us KNO3, and we're also going to get PbI2. So before we go any further, let's figure out if this is balanced. So 1 potassium, that's good. 1 iodine, that's good. 1 lead, that's okay. But look right here, I have 2 nitrates, so I need to fix that. So let's get 2 nitrates. Okay, so now we have 2 potassium, so I got to fix that. Now I've got 2 potassium. And, I need to have 2 iodine. Well, if I put a 2 here, that messes up. That's a clue we did something wrong. So this is not the correct formula for lead 2 iodide. What is the correct formula for lead 2 iodide? PbI2. So that's a mistake I made earlier. But you can catch yourself on those if you see something wrong with your balancing. So that would be a 1 in front. Now let's double check. 1 lead on each side. 2 iodine. Now I've got 2 iodine. I have 2 potassium because that 2 multiplies through, and I have 2 of that nitrate group because that distributes through. So this is going to be my balanced reaction, but we still have not discovered whether or not this will actually be a real reaction. Okay, so to figure out if this reaction works, if it goes, we have to look at your solubility table. You got to look at the solubility table. I'll pause for a second. Okay, so let's look at the solubility table. So on the left, we have all of our different metal ions, and just, make a check here. I give you both the Roman numerals and the Latin names. You don't have to know the Latin names end in the usinic, but that's just there if you want it. And we also have all of the polyatomic and other anions. So we had potassium iodide first. So if we want to find potassium iodide, it's under P, unfortunately. Okay, potassium iodide. And we're going to go all the way across. And do you see that potassium iodide is aqueous? That means it will dissolve in solution. So we can figure out that the first thing we had right here, this was an aqueous solution. Please add that subscript. We also had lead 2 nitrate. So let's go and find lead 2 nitrate. So lead 2, where's lead 2? Lead 2, and then nitrate. Need to go across till we find nitrate. That's also aqueous. Good. That makes sense because all of our double replacement reactions take place in an aqueous solution. So we have an aqueous plus an aqueous. When you look at the possible pairings, metal and nonmetal, the letters in the chart are telling us what they will be. So for this to actually be a reaction that produces something new, I have to get something new. It has to be a new solid, has to be a new gas. If you get aqueous and aqueous, there will be no reaction. Both remain ions in solution. You could write NR, which means no reaction, or you could write NVR, which means no visible reaction. Each is fine. Or you can just put an X through the yield sign. If you get any other letters besides aqueous, there is a reaction. You'll get a solid precipitate or a new gas. Occasionally, you also will get liquid water produced, and that will be usually in an acid-base reduction. So, like I showed you up there, we had to go through and figure out what we had first. There were 2 aqueous. Now we got to figure out the state of matter for potassium nitrate and lead 2 iodide. So let's look for potassium nitrate now. So here's potassium, and then nitrate is aqueous. So right now, we do not know if this is a reaction because this is aqueous. For this to work, lead 2 iodide has to be a solid. So let's go back and check and see, is that a solid? So we've got lead 2 again, and we're looking for lead 2 iodide, right? Yep, lead 2 iodide. So where is that one? That one is going to be right here, and it is a solid. That means I just created a new precipitate, and so this reaction will work. And how do you know this will work? Because you just produced a new precipitate that will rain out of the solution. So that's the new precipitate, which is what the notes really went over down here. So KNO3, not reactive, gets aqueous, no good, but you will get the solid precipitate. So this reaction is a go. So you need to make new compounds using ions and then balance, which we already kind of did. I did those together. So we have Ki plus PbNO3, and remember we said it was an aqueous Ki plus an aqueous solution, lead nitrate. Some number of that will give us potassium nitrate, which we discovered from the solubility table is aqueous. That's a 3, sorry. Plus, that will give us lead 2 iodide, which we have discovered is a solid precipitate. So that's what's important. We bounced up ahead, but let's just do that again. 2 nitrate right here. You need to give me 2 nitrate. That makes 2 potassium. Well, I need to get 2 potassium. That gave me 2 iodide, which is what I needed, and check, lead works out. So this is a chemical reaction that is balanced. Last step is to write those symbols. I like to do that in the middle, honestly, as you're going through and working it out. It doesn't really matter as long as it gets done. AQ means aqueous or aqueous. It is soluble. That means it will dissolve in water, like Kool-Aid powder dissolves in water to make an aqueous solution of Kool-Aid. If there's an S, it is a solid precipitate. If there's a D, if you go back on your chart, D means it will decompose. So maybe it forms but then immediately decomposes. We saw a couple of those examples in the Chapter 8 lab. If there's G, it will form a gas. And you'll see there's a couple other things. Some are partially soluble, some are aqueous but then decompose quickly, and some cannot be made through this reaction. That doesn't mean they don't exist, it just means that they can't be made this way. So just take some time and make sure you understand how to read this chart. And you will have this chart laminated for all your tests. So let's go through a couple more examples. So we have sodium chloride and silver nitrate. So let's break it up into the ions. We've got Na plus and Cl minus. And we have silver, which is always a 1 plus, and we have nitrate, which is polyatomic. So then I like to just show my new ions. So sodium was with chlorine, it's going to go with nitrate now. Silver was with nitrate, it will go with chlorine. So let's write out the reaction. So I got some number of sodium chloride, some number of silver nitrate will now produce, let's just go in order here. So sodium, Na, when that crosses with nitrate, a 1 plus and 1 minus, it's just an NaNO3. Plus, let's see what's left over. Silver, Ag, and then chloride, a 1 plus and a 1 minus. There we go. Now, we're looking at these, your reactants for double replacement usually are always going to be soluble. So I know that this is aqueous sodium chloride, and plus you know that table salt dissolves in water. And silver nitrate, you've seen it in the lab before, it's also aqueous. Now we got to figure out what each of the products are. I need to have at least one new thing to make this a reaction. So let's check our table. We have sodium nitrate, So let's see, where's sodium? And then nitrate is right here. That's aqueous. So is it a reaction? We don't know yet. All of our hopes hang on silver chloride. So let's find silver. So here's silver, and going across to find chloride right here. So that's where I'm in the chloride, and where silver crosses, it is a solid. So yes, this reaction is a go because I have a new solid precipitate. Oh, this is so easy to balance. Look at it, guys. There's just one of every single thing. Remember, you can balance the polyatomic as a unit if you want to, and all your coefficients are just one. Do you really need to write the one? Not really, but let's do it just for practice right now. And we've got one more example. Okay, we got sodium chloride, which we already saw is going to be an Na plus and a Cl minus. We have potassium nitrate, a K plus, and an NO3 minus. So this is going to produce a new compound. So sodium is going to now be with nitrate, the metal with the non-metal. Oops, forgot my charge. And then potassium is going to now be with chloride, a metal and a non-metal. So let's go from left to right. So now instead of sodium chloride, we've made sodium nitrate plus, now we have potassium chloride, so plus KCl. I know from my previous problem that sodium chloride is aqueous, and then potassium nitrate, I had that one yet? No, I haven't. But what you're going to see is potassium a lot of times is aqueous, and nitrate a lot of times will be aqueous. So let's double check it though. Potassium, go all the way across to nitrate, that is aqueous. And then sodium nitrate from the previous problem, you already know is aqueous. No need to double check that. Now, if potassium chloride is solid, that means it'll be a go. If it isn't, that means nothing happens. So let's check. Potassium chloride, it is aqueous. So that means that nothing will happen. What's going on like a molecular or ionic level, these ionic compounds are just turning into their ions. This is basically an ionic soup. We got a bunch of cations, not soups, just soup. A bunch of cations, a bunch of anions, and they're floating around and not reacting with each other. So you could put an X through this. You could write no reaction. Some people will say no visible reaction. So this one will not go. And is it balanced? Even though it's not a reaction, let's make sure it's balanced. Yes. We got a 1 plus and 1 minus. So I'm hoping that that has gone through and given you a good idea. I want you to pause the video, go through and try all these practice problems, unpause it, come back and check your work. Thank you for pausing. So let's look and check your work now. First thing I did, I separated into my ions. So here is your ionic soup. Now you've got to write the equation, balance it, and check your scripts. So we have tin 4-acetate plus 4 potassium hydroxide, both aqueous, will produce tin 4-hydroxide and 4 potassium acetate. I got all of these subscripts by going to my handy dandy solubility table. You will have that on the test. And some hints to kind of pick up on. Acetates usually be aqueous. So if you look at your solubility table and look down that whole acetate list, aqueous, one solid. Some that decompose. And also a lot of things will be aqueous. For example, most of your alkali metals, so most of your sodiums will all be aqueous. Most of your potassiums will all be aqueous. And you'll kind of start picking up on those patterns. Most of your oxides are solid. A lot of your lead compounds based on the charge could be solid. But you can always check the chart. So then there's your balanced chemical reaction. You do well? Good. Number 4, here's my ionic soup. You gotta know those polyatomics. And then here's my balanced chemical equation. Pause this if you need to stop and check your coefficients and your subscripts and everything. But we have 2 aqueous compounds, and we will get solid calcium phosphate. That means the reaction happened. It will precipitate and rain out of the solution. Okay, number 5. Here is your ionic soup. And when we mix together, you will get a solid zinc carbonate. If you check your solubility table, zinc carbonate, it will be solid, so this reaction will go. Number 6. This one's a little funny. You might notice that aluminum sulfate says it can't be made through double replacement, but it does exist, so we're going to carry ahead. But my products, I get aqueous, no reaction. And we've got 15 seconds left, the very last one. No go. If you check your solubility table, you get a star by iron 3 carbonate. So if you have iron 3 carbonate, when you look at that one, let's see, it's right here, it cannot be formed. So it exists, but not from this